Okay, so now let's do three examples. The first one is a control volume. So, and you see there's an inlet, and at the inlet, there's fluid flowing inside into the control volume. But this time, at the inlet, the velocity of the fluid is uniform, and normal to the inlet surface. Okay, first one uniform, second one normal. What does uniform mean? Uniform means if you choose any point on the inlet surface, the velocity has the same magnitude. So that's why when I drew the lines at the inlet, I drew them with the same length, indicating the value, the magnitude is the same everywhere. So that's why we call it uniform. And second one, normal. This one is pretty straightforward to understand. That is perpendicular to the surface. If this is the case, mass flow rate is very easy to calculate. You can directly use this equation. M dot is equal to rho times V times A. Rho is density of the fluid, V is velocity of the fluid at the inlet, and A is the cross-sectional area of the inlet. That's case number one. And now let's take a look at a different case, case number two. You still have a control volume, and then you still have an inlet. But this time, the velocity will be uniform, but not normal. Not normal anymore. It's not perpendicular to the surface, but at an angle. So we can draw it like this. Uniform, meaning the magnitude of the velocity at each point is the same on the inlet surface. Not normal, so the velocity comes at an angle. So now, if we tell you the angle is theta, what should be the equation that you use to calculate mass flow rate at the inlet? Do we still use m dot equal to rho VA? No, we cannot do that anymore because V, the velocity V, is at an angle, and not all of the V goes into the control volume. Why? You will understand better if you do this. You separate the velocity into two components. The first component is the horizontal component, and the second component is the perpendicular component. And which component is actually going into the control volume? The horizontal one. So the velocity you should use here is not v, but the horizontal component. Okay, so now let's go back to the notes. The v you should be using is vx, velocity in the x direction, not the perpendicular in the y direction. Okay, so how do we write Vx? It's gonna be V times, this one is V, so V times cosine theta, and then times area. This is the case number two, when the velocity is uniform but not normal to the surface. And then we have case number three. Still, you have a control volume, and this time the velocity is non-uniform and not normal either. Okay, so it can be anything like this, not uniform and not normal. So what should be the equation we use to calculate mass flow rate? So density will still be constant. You can keep it. Velocity Vx is no longer a constant over the surface area. So what you do if Vx is not a constant over area like we did before, you change multiplication into integration. So it becomes Vx times dA. And you do the integration over the whole surface. So that's the three cases for this course. First one, uniform and normal. Second one, uniform but not normal. And third one, none of them. Not uniform and not normal either. Okay, so you can see the difficulty increases with each one. All right, but the good news is in this case, we only deal with uniform and normal, which is case number one. So mass flow rate in this class will always be calculated as rho VA. Okay, if that's the case, we call it 1D, 1D fluid flow. Okay, one dimension.